the opportunity to speak to an interesting group. This is you're a group of people unlike most that I speak with, because you come here presumably knowing something about what crowdsourcing is, and I often find myself talking with people who don't, so the first thing I have to do is sort of explain what that is. So that also makes me really nervous too, because you're gonna be able to ask intelligent questions.
Great. So
okay,
you have your slides here. So
okay.
I'm not sure if the clicker works, but we'll figure out soon.
Yeah. Do you remember the clapper? Maybe. Let's see. Maybe I'll just use the keyboard. Aha. So most of us are familiar with this expression, don't put all your eggs in one basket. But we do it all the time anyway, right? And particularly when the payoff is really big, even when the odds are stacked against us, then we're all in. And this is exactly the situation today with artificial intelligence. I'm not just being cheeky here, by the way. There's actually a church of AI. I just discovered it on the internet. It's in Silicon Valley. It's called Way of the Future. If you don't believe me, you can look it up. So we have big problems, wicked problems, multifaceted problems involving complex interdependent systems. Things like climate change and geopolitical conflict, and some of these are actually secondary to our own innovations. So, we've created, medical technologies that have, increased our population and urban planning, so we have increased population density. This gives viruses more opportunities to recombine into deadly forms. And of course, we invented air travel, which makes it easy to spread these viruses around the world and increases the risk of pandemics. But what if we could build machines that were super intelligent, had superhuman intelligence? Maybe those could save us from all these problems. I mean, that would be a huge payoff. Or they might destroy us. So, do we really want to put all our eggs in that basket? So you might recall this other handy expression. There's safety in numbers, right? Not so much anymore. So it used to be when one person started to act up, the village would come together and intervene. And at that time, the group was more powerful than the individual. But thanks to the democratization of technology, individuals are becoming more and more powerful. And with population growth, statistically, it's more likely that a single actor who's misguided will seize and abuse this kind of power. So speaking of backpack nukes, does anyone know why the internet was created in the first place? So back in the 1960s, supercomputers were a new thing. I mean, your iPhone is probably more powerful than those supercomputers now, but at the time, they were all the rage, and we needed them to support tactical nuclear warfare. And there's a reason we spent money developing these things. But there was this teensy problem called first strike advantage. So the problem is, a surprise attack that knocked out our supercomputer would make it possibly impossible to retaliate. So as horrific as it sounds, this actually made a preemptive strike kind of a good idea. That's not exactly what you'd call a stable geopolitical situation. So enter Paul Barron. Paul Barron was a RAND analyst who had this crazy idea of connecting all the supercomputers, not that we had very many, but to these geographically distributed supercomputers, connect them all together through a redundant network. And the basic idea was, in the event of a preemptive strike that knocked out a few of our supercomputing nodes, that we would still have, through this redundancy, the availability of information necessary to retaliate. And this actually created the circumstance of mutually assured destruction, which even today continues to be a deterrent for nuclear war. And by the way, Barron's resiliency methods are embedded in the DNA of today's internet. So Barron's idea might have been an ingenious one, but it wasn't a new one. Nature's evolutionary engine actually gave rise to distributed information in natural neural networks. And this is exactly why stroke patients can regain lost memories. So often it's the damage is localized, not in a way that destroys the memories, but just to the retrieval mechanism. So how did this decentralized kind of information processing architecture in the human brain arise in the first place? So let's rewind about 3 billion years to the first signs of life, ancient bacteria. And this emergence of life marked the beginning of information processing in the known universe. But why is life tantamount to information processing? So consider the complex information processing involved in reproduction and how that information guides the development of an organism. And early bacteria also had the ability to respond decisionally to their environment, to stimulation, light and chemicals and magnetism. And ultimately, this ability was sufficiently useful that specialized information processing cells called neurons evolved. And over time, networks of these cells, brains, became increasingly complex and grew in size. But why? I mean, what was the adaptive benefit of sophisticated information processing capabilities? So imagine you encounter a strange creature in the woods that you've never seen before. Okay, so you have to make a decision. You know, do I fight? Do I run? If you make the right decision, okay, you'll survive. That'll reinforce your prediction about what would happen based on that action. If you make the wrong decision and you're lucky enough to survive, then you might revise your predictive model. And then that improved model, that updated model, would hopefully help you in your next encounter. So better predictions lead to better decisions. Now the human brain is amazing. The most complex information processor in the known universe. It's really good at making predictions under a wide variety of circumstances, even changing circumstances. But it doesn't seem to be quite sophisticated enough to solve our hardest problems. And for that, we might need superhuman intelligence. So what if we could somehow create a more complex information processor than the human brain by linking a bunch of human brains together? But how do we do that effectively? We might need something that can sort of coordinate the thinking so it's effective and purposeful, like a crowd operating system. But would such an operating system be powered by humans or machines? So when you think about an operating system, one really useful thing we found in operating systems is the ability to do symbolic processing and reasoning, which allows us to also do logical analysis, that kind of thing. So human brains are actually pretty bad at this. I mean, we can add a couple numbers in our head. If it's me, make sure they're small numbers. And by the way, this is a huge accomplishment for neural networks. I mean, this is rare in the animal kingdom to be able to do symbolic processing. This is why humans have language, is because our neural networks, which were never designed for symbolic processing, got so complex that we can do this. But compared to machines, we're horrible. But machines are great at this. I mean, that's why we created the calculator. Even simple machines are good at symbolic processing. And for this reason, they complement our thinking style. So maybe you've heard about how some people are either left-brained or right-brained. So if you could be a left-brain analytical thinker or right-brained intuitive thinker. So in this kind of space of humans and machines, humans are definitely more on the intuitive side of things. And so we can sort of imagine a left-brain, right-brain partnership between machines and humans, where we lean heavily on the machines for the symbolic kind of processing, but then we rely on humans to do more of the abstract reasoning and bringing world knowledge and a context to problem solving. And there's a beautiful example of this kind of human ingenuity. So there's this, I don't know if you've heard of this before, there's this car mechanic who watched a YouTube video about how do you get a cork that's been pushed into a wine bottle out, and you do it by inserting a plastic bag and inflating that bag, and it somehow pushes the cork out. And he had the idea of using that same technique to get stuck babies out of a birth canal. And this is actually now an FDA-approved product based on his idea. Okay, try to get a machine to come up with an idea like that. But to humans, it's second nature. I mean, he actually had this idea in a dream. And on the other hand, when it came to actually designing and testing it, a lot of computers were involved in that part. You got to keep track of all that stuff and do the statistics. So it's that partnership was actually useful to that. So there's this emerging field called human computation, which tries to understand the respective strengths of humans and machines and how they could be applied to human-machine partnerships. And the idea is to combine these abilities in a decentralized information processing network that, with the goal of creating unprecedented problem-solving capabilities. So over the past decade or so, we've seen some interesting examples of human computation systems. Some of them are passive. So in this query-based syndromic surveillance, they found that actually by looking at the prevalence of Google search terms like cough, fever, sore throat, using keywords that people would search related to influenza, that they could actually predict the onset of the influenza season as well or better than the best CDC model. But some of the most effective examples of human computation are engineered systems like Foldit. So Foldit, the goal of Foldit is to understand how complex proteins fold to determine their shape, because their shape determines their functional characteristics and the pharmaceutical approaches that could be used with these proteins. And basically, Foldit crowdsources the analysis of how to fold these proteins through an online puzzle game. And it actually involves a partnership that takes the human creative component and combines it with a brute force capability of the machine to do different permutations. And Foldit actually One accomplishment was a discovery that eluded scientists for something like 50 years that's revised our understanding of HIV. Another application, so some are more disease-specific. This is a project I happen to be involved in called stall catchers, and the idea here is that we're trying to accelerate Alzheimer's disease research, and so we created an online game that anyone can play, and by playing the game, you're helping the Cornell scientists, the biomedical researchers, analyze mountains of data up to 10 times faster than they could in the lab. That's the goal anyway. Today, our stall catcher players are collectively analyzing the data about 4 times as fast as the lab. And this is actually another example of a human-machine partnership in the sense that we have machine learning algorithms that will look at these blood vessel images, create an outline around each blood vessel segment using computer vision, and then a human looks within that outline at an individual blood vessel and tries to decide if blood is actually flowing or stalled within that vessel. So it's the combination of the machine pre-processing and the human post-processing that results in the needed analysis. Patients like me is what we would call a virtuous ecosystem. The idea here is that it's to help patients with chronic diseases. So if you're a patient with a chronic disease, you can go online and you can see aggregate information provided by other patients in many nice visualizations and graphs and statistical forms, and you can say, oh, this is a popular treatment that's actually pretty effective. I'm going to give it a try. And so then your offline behavior is influenced by the aggregate information online, but then you take your results back into the aggregate. And of course, this leads to the most promising treatments getting the most attention and the most new data. Some new civilian-based counterterrorism systems employed in the Middle East are starting to restore the balance of power in favor of groups. So they combine human-based observations with remote sensors to help predict the timing and triangulate the trajectory of missile strikes to help keep innocent people out of harm's way. So in the future, we can imagine more sophisticated problem-solving systems, systems that might allow us to explore solutions and test those solutions in a predictive model that's a shared collaborative environment, and maybe test out whether or not there are secondary or tertiary effects before we actually implement those candidate solutions in the real world. And these systems will derive their power from increased integration of life and machine processes, vastly distributed and acting, sensing, and thinking in shared virtual and physical spaces. And thanks to our technosocial infrastructure, thanks to the Internet of Things, and new human and machine interfaces like augmented reality, we're starting to see a global superorganism come together. So we're boldly leaving our egg baskets behind, and we're moving toward decentralization, which increases our information processing capability, our resiliency. It distributes risk. It restores power to groups. And it helps enable powerful human-machine collectives with the potential to solve wicked problems today. And most importantly, it keeps humans in the driver's seat. Thank you.
Thank you.